Have you ever noticed that low-energy fluorescent light bulbs are white? Maybe you just wondered what fluorescent means. We need to look at energy and atomic structure to explain this. You may recall that electrons are found around the nucleus in discrete and well-defined orbits or energy levels. The lowest energy orbit is found nearest to the nucleus. In this diagram, orbit 1 is the lowest energy and orbit 4 is the highest. Notice how the gaps between the energy levels are not constant, but become smaller as you move away from the nucleus. Electrons may move from lower to higher energy levels if they receive an amount of energy exactly equal to the size of the energy gap. This is to do with quantum theory, which you may wish to research more by yourself later. The energy needed is easily transferred to the electron in the atom by a suitable part of the electromagnetic spectrum. Let us look at one such interaction that leads to an electron transition between energy levels. When exposed to a certain wavelength of light, an electron can move from a lower to a higher energy level with the atom. We say that it has changed from a ground state to an excited state. This excited state is normally very short-lived, and the electron will fall back down, returning to the ground state. But in doing so, must emit the same wavelength of light that it had absorbed earlier. Let's use a more simple way of showing these transitions by drawing only the energy levels themselves as straight lines and not circles. Now we add another energy level. In this example, the electron has moved from the bottom to an energy level 2 levels higher, and then returned again to ground state. The atom will have absorbed and then re-emitted the same wavelength of light. But what if it doesn't fall back to ground state in one step? Here, there is a 2-step return to the ground state, and so the atom emits 2 different wavelengths of light, each with a longer wavelength than originally absorbed by the atom. This is fluorescence. If the absorbed electromagnetic radiation is in the invisible ultraviolet part of the spectrum, or short wavelength, then the light emitted will be of a longer wavelength and be in the visible part of the spectrum. If tonic water that contains quinine is exposed to UV light, it glows with a blue colour. This graph shows the wavelength of UV that quinine absorbs, mainly around 350 nanometers. The excited electrons in quinine return to their ground state in stages, emitting a longer wavelength of light, mainly around 460 nanometers, the blue region of the visible spectrum. Similarly, fluorescent light bulbs generate UV light, which makes a mix of chemicals in the white inner coating fluoresce, simulating white light. If atoms are exposed to UV light, then electrons in higher energy levels may easily be promoted to such a high energy level that they will have effectively left the atom. This produces ions, and the process, not surprisingly, is called ionization. This is why UV light is dangerous to living tissue, as creating ions, or charged atoms, in cellular genetic material can profoundly alter the chemistry of a cell, causing harmful mutations.
Please like and share our videos with your friends. If you have any questions that you want help with, just comment below.